reactor, how does the presence of moderator cause a change in reactivity? So to start off with, the moderator, when it's water, is largely it's just the hydrogen, it's the protons. The protons are a moderator for neutrons because they have almost identical mass, and that makes them really effective at slowing down the neutrons. And the reason why is if you think, as an analogy, billiard balls. If I have a billiard ball and I try to slow it down by running it into ping pong balls, it's going to have to push out a lot of those ping pong balls before it really slows down. And so the ping pong balls aren't really that effective. Likewise, if I were to use bowling balls, the billiard ball would just bounce off of a lot of bowling balls before it really slowed down very much. But if I put the billiard ball into other billiard balls, then that will very effectively slow down that billiard ball. Because on average, I'll lose about a half of the kinetic energy every interaction. And in principle, in one interaction, I can stop that billiard ball and send the proton that the neutron scattered off of reeling through the material with the energy that neutron had. So protons are really effective at slowing down neutrons. Now, the reason why that moderator is needed in a nuclear reactor today is because the fissile cross-section of the uranium-235 just exponentially increases when the neutron energy decreases. And so I can get the fission probability really, really high if I slow down the neutrons. Now, there's a limit to that. You might think, well, the slower it is, the better it is. Not quite, because when those neutrons get really, really slow, the protons in the water act like a poison. They'll absorb the neutron and become deuterium. Now, deuterium, it's a naturally occurring element, or isotope, sorry, in the environment. But it's at a very, very low concentration, so you don't have a whole lot of it in water. And so if I get the neutrons too slow, then the water becomes a poison, a neutron poison. It starts absorbing the neutrons, and it takes them out of the neutron economy, so they can't go ahead and make fission and keep the process going. And so there's a balance. There's a sweet spot where you're just at the right amount of moderation to thermalize those neutrons and get the most amount of fission for each neutron at that point. And so what we do here in the West with our designs is we keep them just slightly under moderated. So if I put in a little bit more water, then the reactivity will go up a little bit. But the point is that that's at the maximum water content. So when I have regular water, which for all intents and purposes is an incompressible fluid, when I fill the reactor core with water at slightly under moderated, then I can't get more reactivity by putting more water in, because I'd have to crush the water in a way that it won't be crushed. And what that does is it means that if I lose any of the water, the reactivity goes down. I need that water in there to keep the reactivity at a maximum. And so that's where the void coefficient comes in. If I have boiling, if